So far we have discussed several aspects of Gaussian elimination. Now we will go beyond Gaussian elimination and we will learn another direct method, that is the LU decomposition. Here LU stands for lower, upper. Let us see what it is, starting from the ideas of Gaussian elimination. In Gaussian elimination, we start with Ax equal to b, and then at the end of forward elimination, we come up to a situation where Ux equals b prime. Here U is the upper triangular matrix. We know that this b prime is em minus 1 etc. up to e1. These are elementary matrices and a permutation matrix P multiplied to b. And similarly U is em minus 1 up to e1 into permutation matrix into A. Now we can clearly write PA is E inverse U, where E is the product of all the permutation matrix. And we will see in our discussion that this E inverse will be a lower triangular matrix, which essentially tells us that this PA will be now L multiplied by U. And we'll also see in this discussion that breaking a matrix in a lower and upper triangular matrix gives us certain interesting ways to solve linear equation. So let's see what we have in this lecture. In general, matrix decomposition or matrix factorization is an important technique in matrix algebra. It is used for many different purposes. It is used for, of course, for linear equation solution, but there are many other purposes for which it is used. In the later part of the course, if we have time, we will talk more about matrix decomposition. But the idea of matrix decomposition is that we take a matrix A and we break it down into product of several matrices, and we break it down in a way that is beneficial for us. Now, LU decomposition is a process through which we take a non-singular matrix A and we break it down into a lower and upper triangular matrix. If we know the lower and upper triangular matrix corresponding to a matrix A, then solution of this problem Ax equal to b will be very easy. Why? Let us just see. Let us say that for this situation Ax equal to b, we know that A can be expressed as LU, and we know both lower and upper triangular matrices. Therefore, we can write this system as LUX equals B. Once we have written LUX equals B, we can now split the system in two parts. The first part is LY equals B and Ux equals y. So essentially we take this Ux and we write it as y. So now look at the two systems. Please remember that this L, U and B are known. Since L and B are known, we can solve Ly equals B and we can find y from here. Once we know y, we can go to Ux equals y and we can find x here. Now this is an interesting procedure because you see that we are solving Ly equal to b and you are solving Ux equal to b, but both this L and U are triangular matrices. So essentially these are just very simple calculation. There is no elimination process involved here. In upper triangular matrix, you start from the bottom and then go one step at a time and go up to the top. In lower triangular matrix, you start from the top and then you solve for y1 first, then you get y2, y3 etc. You come up to yn. So this is how we can get very easily, we can solve for x. Y is of course an intermediate variable here, we don't need that vector. All we are interested about this unknown vector x, and we can get x in two steps, but we can see that none of these steps require elimination. These are just very simple calculation from triangular matrix. However, how we are going to get the lower and upper triangular matrix from A? Now this is a serious question, and this question will not really answer in this lecture. We have to wait for some time. But in this lecture we will go slightly deeper into this process, how we are getting into this idea that we have just described. Remember our example of Gaussian elimination of this simple equation, that is 3x plus 2y equal to 5, 4x plus 5y equal to 9. We do the forward elimination, eliminate x from second equation. We have 7 by 3, y equals 7 by 3. Then I go toward back substitution. From equation 2 I get y equals 1, and then I use y equals 1. From equation y I get x equals 1. You can verify putting 1 in place of x and 1 in place of y. You can verify that it will satisfy the equations. Now I can write this entire process in matrix form in a way that I start from this 3, 2, 4, 5 coefficient matrix multiplied by the column vector xy equals column vector 5, 9. And at the end of forward elimination, it is transformed to 3, 2, 0, 7 by 3 coefficient matrix multiplied by the column vector xy equal to the column vector 5, 7 by 3. As usual, there is no change in the top row, which means the equation 1, but equation 2 changes. Now we also know that this coefficient matrix 3, 2, 4, 5, it is changing to 3, 2, 0, 7 by 3. This is because we are having an elementary operation here, or we are multiplying the matrix A through an elementary matrix E. And this elementary matrix here is 1, 0, minus 4 by 3, 1. If you don't understand how we are doing this, you can go back to our old lecture and verify. 1, 0, when it is multiplied with this 3, 2, 4, 5, the product will be, top row will be 1 multiplied by top row of A plus 0 multiplied by bottom row of A, which means it is just the top row of A, 3, 2. Minus 4 by 3, 1 means minus 4 by 3 of top row, 1 of bottom row, and that will give us 0, 7 by 3. So we have taken this elementary matrix, multiplied with the original A matrix, coefficient matrix, and what we have is an upper triangular matrix. So we can write this elementary matrix into A matrix, the original coefficient matrix, equals U. This is the operation. Now you see that the elementary matrix E must be always lower triangular. Why? Because you see that nothing happens in Gaussian elimination to row 1, which means in the elementary matrix the top row will always be 1 and 0. And then in the bottom row, we know that the bottom row always have 1 in 2, and then anything that is acting over it is coming from the top row. So top row has certain multiplication factor, and then bottom row is 1. So it is essentially a lower triangular matrix. And you can see that this is a simple example, but you can see that taking a larger matrix, a 3 by 3 or 4 by 4 matrix as an example. So now that we have an elementary matrix here, which is a lower triangular matrix, 1, 0, minus 4 by 3, 1, and 3, 2, 4, 5 here, we can now see that this EA equals U. I can write A equal to E inverse U. And now we know that E is 1, 0, minus 4 by 3, 1. We can find this E inverse using, there are numerous methods to find this inverse. You can use any of this method and see that E inverse is 1, 0, 4 by 3, 1. The numbers here are not important. What is important is that this is a lower triangular matrix. E is a lower triangular matrix and its inverse is also a lower triangular matrix. So we can say that A matrix which was E inverse U. E inverse is a lower triangular matrix L, and A is LU now. So A is broken into LU. My L is 1, 0, 4 by 3, 1, and U is 3, 2, 0, 7 by 3. This looks very nice, but now we will generalize it for a larger system. We know that for any invertible matrix A, we can go with the Gaussian elimination, and in Gaussian elimination, we multiply with a series of E matrices, that is the elementary matrices, and let us say that their product is this capital E. So capital EA equals U. Now when we are doing forward elimination, we are taking this rho I is rho I plus certain factor multiplied by rho k, and this rho k is certainly less than I, which means that, let's say that in forward elimination we start from 1 as my pivot. So A11 is my pivot element. When I am operating over row 2, it should be row 2 plus certain factor multiplied by row 1. So this k is always less than I. Because this k is always less than I, when we write this particular operation in terms of pre-multiplication with an elementary matrix, always this factor will come here, and then I will have 1 for this row I. So I have 1 here and I have factor here. Factor will always come in the left side. Factor is in the left side of 1. Always it will happen, and then right side it will be all zeros, which means that this E1, E2 up to EM matrices are always lower triangular. Now we argue that when all these matrices EM to E1 are lower triangular, then their product E is also lower triangular. And if E is lower triangular, we argue that E inverse is also lower triangular. But why it is so? I will answer this question shortly. So if E inverse is lower triangular, this E inverse EA equals U now gives us A equals L into U. So now we have decomposed A into L and U. So if we can do Gaussian elimination for Ax equal to B, we should be able to do LU decomposition of Ax equal to B type system. We are only arguing that point here. This is not the way to find L and U, and there are other processes and we will see it later. This is not an efficient process of finding L and U, but we can see that how these lower and upper matrices are coming. Now take a case when we are using partial pivoting. It's not just Gaussian elimination. So if we use partial pivoting, then you know that this U matrix is now there is a series of E matrices. These are elementary matrices, and then there is a P matrix that is a permutation matrix. Similarly, the B prime that is coming on the right hand side, we have a series of E matrices multiplied by permutation matrix multiplied by B. When we multiply by permutation matrix, it will lead to row exchange in A and also row exchange in B, of course, but we are mostly interested about row exchange in A. And we have also discussed that when we multiply many permutation matrices, the product will be again permutation matrix. So this P is essentially a product of many permutation matrix. In the course of forward elimination, we may have to do partial pivoting several times. So every time we do row swap, a P will come, and this P that we are showing here, this is a product of all those P's. Okay then. Now for a linear system Ax equals B, we can in general write PAx equal PB. That means we may need to swap rows, and we are doing that by multiplying P. And then this LUX we can write at PB, and PA is my LU. So the idea is that when we have to do row swap, instead of writing A equals LU, we can write PA equals LU. Otherwise, it's just the same thing. Okay. Now we have the idea that if we can have Gaussian elimination, we can have LU decomposition as well. But how do you find the LU decomposition? LU decomposition, so far we have arrived in LU decomposition from Gaussian elimination, but this is not an efficient procedure, because Gaussian elimination itself solves linear system. So it is not necessary to use Gaussian elimination to find L and U and then to solve linear system. That will be of no use. So what we have to do is that we have to figure out some other easier method. What I mean is easier than Gaussian elimination for the L and U evaluation, and then only this LU decomposition type procedure will have any advantage. Another point that I want to make here, that LU decomposition is not unique. Now you think about it, that why it is not unique. What we mean that for a same A we can have different sets of L and U, but you think about it and argue that why is it so? How can we have different sets of L and U? But this is something crucial in finding L and U, and something that we will discuss later on. Now we go back and we take up some of these statements that we made, and let us just argue that how we made those statements. First statement that we made, that if we multiply lower triangular matrices, we will have a product will be lower triangular. So we start from two lower triangular matrices and check if their product is indeed lower triangular. So let us take like two n by n matrices, A and B, both are lower triangular, and another matrix C, it is also an n by n matrix, and this is the product of AB. Element of C are Cij, and element of A and B are Aij and Bij respectively. Until now we don't know what would be the nature of Cij, but we have assumed that A and B are lower triangular, and we will go with that for now. Since A and B are lower triangular, then you know that if j greater than I, then Aij, Bij, both of them will be 0. So i's are rows and j's are location of the columns. So if j greater than I, then Aij, Bij will be 0. That is the definition of lower triangular matrix. And we know that from the definition of matrix multiplication, we have this Cij will be summation over k 1 to n Aik Bkj. Here we know that Bkj will be 0 if k is less than j, and Aik will be 0 for k greater than I. So these are simply coming, this Bkj and Aik, these are simply coming because A and B are lower triangular matrices. Now we see that when we take this into consideration, we see that Cij turns out to be the summation of k starting from j, j plus 1, j plus 2, etc. all the way up to I, Aik Bkj. Any other term that is coming, that will be 0. This is very important. You can see that if k less than j, it is 0. Bkj is 0. So Bkj will be non-zero only if k is greater than or equal to j. So k starts from j for Bkj equal to 0. And on the other hand, if k is greater than I, then Aik equals 0. So k cannot be greater than I, k cannot be less than j. So between j and I, the k will play, and this summation will have any meaning between j and I. Which means that Cij could be non-zero only if j is less than I. K must go from j to I, not I to j. The only way Cij could be a non-zero if j is greater than I, or we can say that this matrix C is such that for j greater than I, Cij equals 0. And this is the very definition of a lower triangular matrix. which tells us that matrix C is lower triangular. Now we have multiplied A and B, two lower triangular matrices, and the product we see is another lower triangular matrix. The corollary is that if we have many lower triangular matrices, is not just two. If we have more lower triangular matrices, then you can multiply two matrices at once, and that way you will see that at the end, no matter how many lower triangular matrices we multiply, the product will be a lower triangular matrix. Now the second statement we made is that inverse of our non-singular lower triangular matrix is also lower triangular. Why it is so? So let us say that we have this A matrix, which is an n by n lower triangular matrix, and we know that because A is a lower triangular matrix and product of lower triangular matrix is a lower triangular matrix, so I can take powers of A and that will again be lower triangular. So the characteristic polynomial by definition is a function of lambda, and that is given by determinant A minus lambda I. So we will have a characteristic polynomial like this, where C's are the constants. Now we can use this Cayley-Hamilton theorem. If you don't remember characteristic polynomial and Cayley-Hamilton theorem, you can just take a look at any linear algebra textbook. These are very simple ideas. You will quickly get, in few minutes you will get the ideas. If the characteristic polynomial is like this, then the Cayley-Hamilton theorem suggests that a to the power n plus c n minus 1 a to the power n minus 1 plus all the way up to c1 a plus c naught identity matrix equals a null matrix. So if I multiply both sides with A inverse, what happens is that I have this A n minus 1 comes here. Here we have n minus 2 all the way up to go C1 becomes A into A inverse. So it becomes identity matrix, and C naught is multiplied by A inverse. So using this equation we can find A inverse, and my A inverse will be given by minus 1 by C naught. Then within bracket I have a to the power n minus 1, c n minus 2, a to the power n minus 2, etc. up to c1 in. This c naught can't be 0 in a non-singular matrix, although it is, there is no need to discuss it now, but you can see if you open up a book that c naught is actually the determinant of matrix A. So it is non-zero for a non-singular matrix. But now you can see that using Cayley-Hamilton theorem, I have expressed A inverse as a series of the powers of A, and A is a lower triangular matrix, and I know that product of lower triangular matrices are also lower triangular. That means A square A is lower triangular, which means A square is also lower triangular, A cube is also lower triangular, etc. So all the matrices that you see here is lower triangular, and at the end this I is, of course, this is the identity matrix. So it has 1 at the diagonal, otherwise it is 0. Overall, it's very clear that A inverse is also a lower triangular matrix. So this cleans up the points that we have made before, that the product of lower triangular matrix is lower triangular matrix and inverse of lower triangular matrix is lower triangular matrix. We can now see that how that are happening. Now we are near the end of this discussion, and here as exercise you can solve this equation using LU decomposition. Right now, of course, you don't know how to find L and U. So what you do, you follow the Gaussian elimination route what I have shown here. Of course, that is an inefficient route, but we are not doing this for efficiency. We are doing this just for the exercise, that how this LU decomposition works. For that, it is quite alright that you follow the Gaussian elimination route and find the L and U matrices, and then you do LU decomposition to solve these two set of equations. Is LU decomposition unique? Well, I have already answered that it is not unique, but you discuss that why it is not unique. Think about it. Don't jump into any book. Look into these notes and think about it, that why it is not unique. Finally, as we all know, I already mentioned that Gaussian elimination is not a good technique for LU decomposition, of course, because Gaussian elimination itself can solve linear equations. Why you are going to use Gaussian elimination for LU decomposition? But what could be other methods? We'll see some methods in next lecture, but before we do so, can you just think about it and suggest something? That's all for this lecture. Thank you, and I'll see you in next class.